So today we're going to talk about geometry of submanifolds, and this is otherwise known as Gauss Codazzi formalism. And the motivation here, well, it's actually twofold. One is that yesterday I derived the metric or the gravitational field of a domain wall. And the feature that we saw about the domain wall was that it was effectively three-dimensional or 2 + 1 dimensional in our four-dimensional universe. So it was something that was lower dimensional, even if it only was lowered by 1 dimension. And so it would be nice to see if we can get a more general description of these lower dimensional objects living in a higher dimensional space-time. The other motivation is this kind of flag that I put up when I described the Einstein-Hilbert action. And we saw that if we varied R root G, then sure enough, it's D for X root G, we got the Einstein tensor. So in the main part of space-time, this would give us the Einstein equations. But we also got a sort of pesky boundary term, which had normal derivatives of delta G in it. So we couldn't, we had to sort of go a bit beyond the conventional variational principle in order to completely use Einstein equations in 4 dimensions. And so what we're going to do today is, well, we're going to develop a sort of general formalism for submanifolds, but then we're going to look specifically at this issue, and we're going to add an extra piece which lives on the boundary of delta M, which is going to give us some boundary variation. So this, a sort of boundary, something that lives exclusively on the boundary times delta GAB on the boundary, minus this piece. So that's what we're going to do. That's where we're headed. So what we have to do first is find a way of properly dealing with submanifolds. So that's what we're going to start with. I mean, another bonus is, of course, that typically we use the action to sort of measure weights or probabilities of particular configurations. And the Einstein-Hilbert action, being the integral of R, vanishes for a huge class of solutions. So it's not that useful if we're going to try to use an action to start, for example, in a partition function. Okay, so the geometry of submanifolds was developed by Gauss and Codazzi. And really, it's a way of taking the tangent space of the manifold and kind of splitting it into pieces that are going to lie within the submanifold and pieces that are going to lie normal to the submanifold. So that's really what it does. It takes geometric quantities and takes the sort of parallel and perpendicular components, essentially. So that's what we just need to sort of define. So here's our submanifold. So I'm going to take my higher dimensional manifold to have dimensions capital D, my lower dimensional manifold to have dimensions little n, and of course what I'm sort of taking as given that basically I've got this submanifold. You can take a local chart from M and just simply look at its effect on sigma, and it's simply saying that what you get is, you know, a C infinity manifold in the sense that we are used to. So we just need to introduce some terminology. So the codimension of sigma is D minus n. And is the number of normals, essentially. So the submanifold sigma, it's a manifold in its own right. So if you just look at it, so sigma there is a subset of points lying within the manifold. So it's a subset of events. So that gives you the bit where the manifold is a set of events. And then if you look at a local chart in M, and then just look at its action on sigma, that'll give you some local coordinates restricted to sigma.
How is this sigma different from a local chart?
So it's just because you're looking at what happens locally down on sigma. Another way that, I've already sort of written something and not explained what I was going to say, is that you can also view sigma, because it's some lower dimensional manifold, you can also view that as having its own functions living. So there's a sort of dual view of sigma in terms of intrinsic and extrinsic quantities, which I'm going to be discussing as we go forward. But you can either view, I don't know whether I should skip ahead or not, but your sigma in M locally looks like a restriction of the coordinates to this lower dimensional space. So it's in the sense that all of these functions are differentiable, infinitely differentiable. So that's the sense in which it is a submanifold. So it's a subset of M, which is itself a manifold in its own right, which means you can construct coordinate charts, et cetera, et cetera, et cetera. So, well, I'll be doing examples. So here, if sigma is defined locally in a coordinate patch, then dx mu by d sigma a, you can visualize that as being tangent to sigma, and so n you visualize as being normal to sigma. So for simplicity, I'm going to choose my normals such that not only are they linearly independent, but they're sort of mutually orthogonal. So this is, of course, assuming we've got a metric on our manifold, although that statement doesn't need it. Okay, so now we just sort of said what we mean by sigma, what we mean by its codimension and the normals. What we now want to discuss is projecting structure from our manifold, or projecting structure onto sigma, or what structure does sigma inherit from the higher dimensional manifold. It's the other way around. So, of course, Gauss and Codazzi didn't have to worry about signs because they would be dealing with completely Euclidean manifolds. But in our case, we're dealing with a Lorentzian manifold. So we essentially, what the first fundamental form does is it takes the metric and it kills off any pieces of the metric that are normal to sigma. So it's subtracting off all the normal components. Mm-hmm.
What is the sum up to?
Sorry, the sum is d minus n. So it's really summing over all the normals.
Right, yeah.
So I've chosen my normals to be mutually orthogonal unit length, essentially. So when I take those components, NIA, NIB, that is exactly the part of GAB which lies along that particular normal direction. So it subtracts off the bits of G lying along the normal directions. Mm-hmm.
So the normals will never be null?
Not in this case. So I'm not going to discuss null surfaces, because there's a degeneracy about null surfaces. But I think you can find a discussion of those in the literature. So I got asked this question yesterday over lunch, actually. So maybe I should go and hunt up the reference for that. Yeah.
So what is the power of minus to the power minus?
So minus to the I is indicating that you need to change the sign dependent on whether the normals are space-like or time-like.
Is the same I as the index that you're sending?
So it's the same. It's telling you whether Ni is time-like or space-like. So, for example, if you were in Minkowski space and you had a surface t equals 0, and you wanted to, then the normal of that would be very simple. It would just be n is dt or d by dt. So nt would be 1, and all the spatial components of n would vanish. So therefore, nt would be plus 1. And so in that case, if I look at HAB, it would be HAB as eta AB minus, because it's time like nn. So n is only ever non-zero in the time component, so that would kill the time component, but leave the spatial components. If it was a time-like surface, so x equals 0, for example, you'd have the plus sign, and of course that would mean, again, nn would be 1, but now gxx is minus 1, so you add 1 to kill it. Okay?
So I understand that, but here it's also because I goes from 1 to d minus n.
Yeah.
So depending on the value of I, the sign will
Could change, yes. So this is allowing for the fact that what we could have is a codimension 2 surface, which is space-like, which would have one time-like normal and one space-like normal. So this is simply allowing a general prescription for a general dimensional submanifold. And I'm just, for this point, this is why I explicitly wrote the sum over I rather than assuming any Einstein summation convention, because there's more going on than just a simple sum over I. So this is what I was just saying. H projects out the components of G normal to sigma, and it gives an indication of the metric that sigma inherits from M. So because sigma is a manifold in its own right, we can also consider intrinsic quantities. So H, although it's projecting parallel to sigma, H is associated with T star of M. It's parallel to sigma, but it's still living in the tangent spaces of the higher dimensional manifold. An intrinsic quantity will live in the tangent or cotangent bundles of sigma. So they're sort of physically equivalent to all intents and purposes, but they are different. So dx mu by d sigma A, which I wrote down before, and sketched that as being parallel to sigma, this gives you a map. So this is coming back to this business of maps and manifolds. So this is the pullback map, such that a one form of the manifold can not only be projected parallel to sigma, but in this case it's actually knocked down into the cotangent space of sigma. So again, our picture, we've got sigma, we've got this coordinate function x mu of sigma A. Here's our manifold, and sigma's inside it. And so that's kind of giving us this notion. Remember, we have push forwards and pullbacks for maps between manifolds. So in particular, I can take the first fundamental form, and in fact, I don't even need to take the first fundamental form. I can just take the higher dimensional metric because, of course, the normals annihilate these tangent vectors to the manifold, and I can literally project down my metric into sigma. So I've got there's sort of two parallel pictures going on here. They're both got the same physical information. H and gamma are in some sense the same, but they're really different tensors. They're living in different tangent spaces. So that tells us how to project the simple structure straight down to the manifold. Now we want to think about connections. So the second fundamental form tells us something about the embedding of sigma in M. So if we have, for example, M is R cubed and sigma is R squared, so piece of paper, I could just simply embed my piece of paper straightforwardly in R squared as a plane, which is just flat. And that's a very straightforward, boring embedding. But instead, I could sort of twist my piece of paper around. That's also a submanifold. You can sort of see it is because I'm actually just doing it in front of you, so I'm not doing anything discontinuous or non-differentiable. I can roll up my piece of paper. I can make a cylinder. I can't personally make a sphere with a piece of paper, but you can imagine a sphere as an embedded surface in R cubed. And all of these are embeddings of a two-dimensional surface in a three-dimensional manifold. But they're quite different in terms of the way they look to us. And this extrinsic curvature is what is mathematically encoding that difference. I can also write it in intrinsic coordinates. Oops, that should be a new. So from the intrinsic expression, what I do is I take my covariant derivative of n, I project it down, but now I'm making use of the fact that n and this projection vector are orthogonal to swap what the grad is acting on, and this new covariant derivative is simply the connection that sigma inherits from M. So the tutorial today is going to explore some of these things a bit more explicitly. Yep.
In the first line, should there be a symmetrization of the capital AB indices?
Yeah, although, yes. Although to some extent, since they're the same vector, it's kind of symmetric. But yes, let me just keep consistent. Basically, as we're going to see, anything anti-symmetric is sort of normal. So a picture of this. If this is a surface, sort of a line on the plane. Here are my normals. And you can see that as vectors on R squared, those normals, as I move along my surface, are changing in direction. So, for example, if I move this normal down here, I get a non-trivial angle. And so that's KAB. KAB is telling me how my normal changes as I move in the submanifold. And so in this case, with a curved embedding, you can see that the normal shifts. The background manifold is completely flat. And in this case, I do have some extrinsic curvature of the embedding. So it's nice to see an example, I think. And we'll look at the example of a cylinder embedded in R cubed. So my first fundamental form, we're in Euclidean space now. So in fact, it's a different set of rules for the minor signs. My first fundamental form is just the Kronecker delta minus NA and B. Now what's my normal? Well, the normal lies in the xy plane, and it's just cos theta sine theta 0 if I represent it in polar coordinates. So my HAB actually looks a bit of a mess, to be honest, if I write it in Cartesian coordinates. So this is sort of beginning to highlight differences between the intrinsic and the higher dimensional expressions. However, of course, I could write this in polar coordinates, which would be a lot easier. And in polars, it looks nice. Now, quite often, we can choose coordinates such that the normal coincides with one of the coordinate directions, like here. The normal is d by dr. And we can choose coordinates such that n exclusively lies along that radial direction. But that's not always possible. So sometimes you have to be a little bit careful if you're dealing with first or even second fundamental forms in situations where your surface does not lie along a coordinate surface, yes?
So when you say in Cartesian or polar coordinates, those are coordinates on the original manifold family?
On the original R cubed, yes. So in this case, and because this is a 3 by 3 matrix, yes. But I'm coordinatizing my manifold M. In the first case, I'm coordinatizing it in a way that is most natural for a flat three-dimensional manifold, which is Cartesians. But that is not a particularly useful coordinate system for a cylinder, because a cylinder has a different symmetry. So sometimes, you know, the surface that you're looking at follows some symmetry of your background space-time, which is great, because then you choose the right coordinates, and the intrinsic, extrinsic, or, you know, pictures are pretty much the same. But that's not always true. And this was really just meant to highlight that. So K, the extrinsic curvature, well, we've only got one normal, so we don't need to worry about those little i's. So let me stick to polars because there's no sense in complicating things. So in polars, I've just got NR, but I do have connection components. So if you were doing it in Cartesians, there would be no gammas, but you would have non-trivial partial derivatives of n. And so if I do this, the only connection I've got in that case is gamma r theta theta, which is minus a. So I get just a single non-trivial component of K. Intrinsic picture. My coordinates are going to be theta and z, where theta is just the polar angle projected down onto the cylinder, and z is the height of the cylinder. So then, my intrinsic metric is now a 2 by 2 matrix, of course, because I'm in a two-dimensional manifold. It's a squared, obviously, depending on how big my cylinder is, the distance in the theta direction will change, but the z direction is always the same. dz is a proper distance up the cylinder. And KAB is now, again, a 2 by 2 matrix, but now it's nilpotent. It's not invertible. So what we see here, or what we're going to see, is that when we first come across the notion, we're first told that a cylinder has zero curvature, a cylinder is actually flat, it always seems a bit bizarre. We think, how on earth could a cylinder be flat? But in fact, the reason is we are, or people, I'm sure by now you know cylinders flat and it's obvious, but that's really picking up this notion of extrinsic curvature. The cylinder is flat, but it doesn't mean that there's no notion of curvature associated to it at all. There is curvature, there's curvature of the embedding, this extrinsic curvature. And so that's the sort of classic confusion.
I was going to ask, if the cylinder is flat, why is the intrinsic K be non-zero?
Extrinsic K. Yeah, no, well, to really see it, we'll have to get to the end of the story of Gauss Codazzi, because at the moment, all I've done is I have projected the metric down, and the extrinsic curvature is like a first derivative. So what we're doing at the moment is we're projecting the connection and discussing that. But in this case, there is some physical meaning to some of this first derivative. It's a curvature of an embedding, and it's something that we intuitively grasp.
Does the pullback on the submanifold in corresponding coordinates always look like a submatrix?
So you mean this, sorry.
AB, the small KAB and the big KAB.
Sorry, I'm not.
So the extrinsic KAB and the intrinsic KAB, the intrinsic KAB looks like a submatrix.
Yeah, it's just I've done this. So the reason that it looks like that is because the coordinates here are r, theta, and z.
Yeah, sure.
So all I've done to get my intrinsic coordinates is I have killed that one. If I had written KAB in Cartesians, it would be a bit messier. It would be more like that. Well, it wouldn't have this piece there. It would be something like this. And so if I were then going to make that intrinsic, I would have to now project down. And this matrix here would be non-trivial, or more non-trivial, because you'd have sort of dx by d theta, dy by d theta, dx by dr, dy by dr. And so it would not be the case that you'd just be able to do a very simple translation. That was why I did it in polars here, simply because we have a coordinate system which respects the symmetry of the cylinder, so why not use it?
So in other words, could I say that H has reduced rank compared to G?
Yes, so because it's projecting parallel to the submanifold, so it has an effect of, it is reduced. If you've got it in the higher dimensional coordinates, and it might not be so obvious that it consists of some of these nilpotent directions plus an invertible subbit, but it's really obvious here. Yeah. So if codimension is bigger than 1, I mean, most of the time I'm going to actually talk about codimension 1 because we're interested in boundary terms for our gravitational action. We're interested often in domain walls. But again, just in the interest of being general, if codimension is bigger than 1, the normals can also vary. So a way of thinking of this is in 3 dimensions, embedding a one-dimensional submanifold. I could take my normals to just simply be the x and y directions and propagate them up and down, or I could be a bit perverse and say, nope, I'm going to rotate them as I move up in z. Completely the same picture, same submanifold, different set of normals. And so we also have a fundamental form. There's lots of fundamental forms here. associated with this. And so this is really like telling you, I mean, in this case, it's obviously a gauge choice. It's obviously something I can choose. And so it's just simply telling you it's like a gauge potential associated with that choice of normals. But if I were to twist my embedding of a line in R cubed, I could then say if I close my circle off altogether, I could then have a normal bundle which just comes back to itself, a normal bundle which twists, double twists, etc., which are kind of distinct choices. Forms, not forms. So the normal fundamental forms take the variation of the normal and project it down, actually transverse to sigma. So I'm going to choose grad n of n, grad ni of nj is 0. That's simply saying that notionally I extend my normal fields geodesically off the manifold. But what I can't do is get rid of any twisting of my normal forms, although that is potentially a gauge choice. What isn't a gauge choice is, of course, the curvature of this connection. So that was what I was saying about, distinct choices for, say, a closed submanifold. So we're not going to do much with these, but it's basically something for a completeness of the picture. If we are thinking of higher codimension submanifolds, we've got the notion that we should be able to project our connection parallel and orthogonal to the manifold, and this is the sort of perpendicular piece.
So does this quantity know about the integrability of the codimension? As in, what I mean is not the submanifold we're interested in, but the one transfers to it.
Mm-hmm.
Does this quantity know about that, as in whether that's integrable?
I'm not sure what you mean by integrability of the normal manifold, but this quantity certainly knows, obviously, about the normal, or at least just about the normal planes, the normal tangent planes to sigma. So if there's any non-trivial structure whatsoever, be it non-trivial because the higher dimensional manifold is curved, or non-trivial because of the way sigma is embedded in M, that's where it will show up. So beta itself is not sort of directly a physical quantity because, as you see, I can sort of sit and twiddle with my normals as much as I want and change locally beta, but I can't change sort of d beta, if you like, d beta plus beta wedge beta, the usual curvature piece. So it knows about the normal pieces of curvature, if that's what you were asking.
In the sense that, the Frobenius sense, that we have integrable surfaces, and we know that the submanifolds find all the machinery that we do.
Yeah.
That those definitely are, but then these needn't be, right?
Yeah, I mean, to some extent, or one thing I'm avoiding, all I'm ever doing is I'm always staying right close to sigma. So, yeah, so I'm not sure how far you can push it out. Yeah. So what we're now going to do is to derive the Gauss equation, which relates the intrinsic curvature of sigma to the intrinsic curvature of the manifold, the bit that it gets because the manifold is curved, plus the bit that it gets because it is curved in the manifold. So I guess the cylinder wasn't a brilliant choice because we're about to derive that the cylinder is flat, but certainly a sphere, for example, embedded in R cubed. We know a two-sphere has curvature. R cubed does not. So there must be, when we relate the intrinsic curvature of a submanifold, there's got to be two parts to it. It could curve because the manifold is curved, or it can curve because its embedding is curved. So this is what we've got to kind of piece together. How do we decide what the curvature is of this submanifold? Got to get my signs right. So the Gauss equation relates the Riemann curvature of sigma to the Riemann curvature of the manifold plus corrections due to extrinsic curvature. So it's more or less what you might guess, or if you tried to write something down with the right number of indices and the right symmetry, this is more or less all you can write, and is also quadratic. More or less, this is the only thing you could think of writing down. But notice what it does is it says, take your higher dimensional Riemann curvature, project it parallel to the manifold. So this is kind of telling you this is the bit that it inherits from the higher dimensional manifold. And then take the extrinsic curvature, and this is sort of like gamma, gamma wedge gamma piece, and take k-squared pieces with the, the correct number of indices and correct symmetry. So this combines the notions of intrinsic and extrinsic, intrinsic of the higher dimensional manifold, and extrinsic in terms of the embedding. So I'm going to prove this for codimension 1. That's where we're really going to be coming up and needing this relation. And the proof involves the use of the Riemann identity. So we're going to take a vector which lies tangent to sigma. So, oops. So that's our Riemann identity. It's simply saying the anti-symmetrized covariant derivative acting on a vector gives you the Riemann tensor. All those very illegible things in brackets are all just ends. It's saying it's the lower dimensional connection covariant derivative. So let's Right, so let me start off. It's the lower dimensional Riemann tensor I want to derive, so I'm going to start by writing that relation down, the Riemann identity. Then I'm going to take these lower dimensional covariant derivatives. I'm going to express them as the higher dimensional covariant derivatives. So you get the lower dimensional covariant derivative by taking the higher dimensional covariant derivative and projecting every possible index down. I'm going to do that. Then I'm going to rejiggle such that I now have a commutator of higher dimensional derivatives, giving me a higher dimensional Riemann, plus some extra pieces. So that's the plan. So the first step so that's just the first line, first definition. So what is this lower dimensional derivative? Well, the first one, I said you take the higher dimensional derivative and project absolutely every index down. So here we've got a C, a D, and an A. So I've got to have an HC, E, an HD, F, an HA, G. Then the higher dimensional derivative. So that's the first bit. I've taken this covariant derivative and projected it. And then I've got to do the same for what's inside the brackets. So at the moment it's just sort of a bit of a slog. We're just sort of putting everything down that we know we need to re-express. But already what you can see is that this covariant derivative here is obviously going to act on the HFP, the HQG, as well as on the V. So the part where it acts on V, if you look at the way the rest of these indices kind of move together, we've got an HCE, we've got an HDP, and an HAQ, grad E, grad P, VQ. And then we're subtracting C exchanged with D. So you can see that this is taking the antisymmetric higher dimensional derivative. So you can see that we've got the higher dimensional Riemann with very little effort. Now we've got to look at the derivatives of these first fundamental forms. So I get two pieces here. So I can, first of all, act on HFP. And then I'm going to act on HGQ. So nothing subtle going on, it's just making sure you write all the terms. So now let me think about what the covariant derivative of H is. Well, H, way up there, was simply defined as G plus or minus NN. And so that means that the derivative of H, so if I put this now just in a little colour on the, little aside, so let me just take n to be space-like, just for the sake of argument. then grad of HAB is simply going to be NA KBC plus NB KAC once you've got all of these other first fundamental forms pre-multiplying it. So I get extrinsic curvatures coming from the derivatives of my H. So now let me look at what the free indices are here. In the derivative of, I'll say it, but then I'll say it again when I write it down. In the derivative of HFP, I'm going to have a KEF times a normal, NP, and I'm going to have a KEP times a normal NF. So the normal NF will hit this first fundamental form here and give me 0. When I look at this, I'm going to get a normal with a G component, which gives me 0, and then I'm going to have a normal with a Q component, which now contracts on the V. So if I look also here, V lies tangent to sigma, so V is just going to be sort of propagated off sigma. So the normal derivative of V is going to vanish. So actually this term is 0 because grad NV is 0. So my Riemann, well, the first term I said was going to give me just the higher dimensional Riemann. So I get the higher dimensional Riemann for the first term, and the last term has only one non-zero piece. Which is an extrinsic curvature piece. But now, because N and V are orthogonal, I can say that this is minus VQ grad P NQ, which is minus VQ K PQ. So, relabeling various indices. I've got the first piece. The first bit is the bit that we want. And then the second bit, so there's a lot of indices going on here. So we've got a V B primed, K B primed, and then that's a P index which comes down to a D here. And then I've also got here K A C. And then I've got to subtract off C interchanged with D. So what I've derived is exactly what I advertised on the board above for the choice. So N was space-like. So for space-like, minus to the I is +1. So I do indeed have KAC, KBD. So this is the right expression once you unravel the indices. So in the last couple of minutes, I just want to quickly return to the problem with the variational principle and looking at how we can derive or add a boundary term to cancel off these normal derivatives of G. So if I want to hold my boundary fixed, so I'm doing my Lagrangian principle, then only the normal can vary. And again, I'm going to choose n to be space-like, just, to not have a load of signs floating around. So if the normal only can vary, this tells me that the variation of the normal is proportional to the normal, and my delta GAB so it means that the variation in the normal is given in terms of delta GAB. So now I want to consider the only sensible thing that I could for a boundary term. Which is to consider the extrinsic curvature as a possible boundary term. So delta K is delta of the divergence of n which has two pieces. It depends on the variation of the normal, and it depends on the variation of the connection. So the variation of the connection is just a normal derivative of delta G, or n dot the variation of the connection. So that's good, because that's kind of one of the bits that we want. And then the other bit I've now rewritten in terms of delta GAB. And now all I've got to do is go through and do that differentiation. Okay, so the covariant derivative hits the first normal. That gives me an extrinsic curvature piece. My normal, if I try taking grad A of either of these normal terms, I get 0 because I assume I extend my GD6 normally. There's a lot of normals going here, isn't there? So the only bit I get is actually taking the derivative of delta G. Now, so I've taken the first and last pieces because they're kind of where I want them to be for now. Now, if I look at this, what I want to do is I want to turn it into this, which means I need to sum over these two indices. So I need to kind of sum over A and C. And I think I've gone and put a... and so what I want to do there is I need to change this NaNC into a G. So if you remember, H is G plus NN, which means that NN is H minus G. So I've got minus a half HAC grad A delta G BC, and then I've got plus a half NB there, plus a half NB grad A. My indices are all over the place here today. Delta G B A. Yeah. So I've got now, this is what I want, this is what I want. I'll hold with this for the moment. And so all that's left is this extra term here. So let me collect together the pieces that I am happy with. So now I'm going to say that this last term is the lower dimensional covariant derivative. So what I've done here is I pull that NB inside, which is where, and then I have to take its derivative, so that's where that KAB comes from. And then what I've got is simply the lower dimensional covariant derivative. So this term now genuinely is a total derivative because we're on the boundary, and the boundary of a boundary is 0. So this gives me nothing because there's no boundary to my boundary. And so what I'm left with is the bit that I want to cancel. I've also got to take into account the variation of root G on the boundary. And so by taking this boundary term, I end up cancelling. If you start at the far end, would be fine. So I've now rewritten it as my boundary term gives me the normal derivatives, which will cancel off, and something which now depends only on delta G, which of course vanishes on the boundary. So this boundary term, SGH, which is minus 1 over 8 pi G integral of K, is the Gibbon Hawking boundary term. So this is how we make our gravitational action properly kosher as a variate Lagrangian principle. I should stop. Yes?
You said that we extend the geodesic normally and therefore those two terms vanish. So basically they're symmetrized.
Yeah, so grad n of n is always 0 because it's talking about stuff which is happening completely in the bulk and is not projecting out to anything on the boundary. So we just choose it. It's easier to say we choose it that way than to sort of demonstrate that it really doesn't matter.